After the era of nucleosynthesis, we now enter into the era of nuclei. The largest particles in the universe, the largest structures formed, are now the nucleus of atoms. Now, during this time, it is still too hot for atoms to form. The electrons won't actually stick onto the nucleus right now. What this means is there's a whole bunch of free charge, a whole bunch of electrons and nuclei. Light interacts very, very strongly with charged particles. What this means is that light does not travel freely. In another way of thinking about it is that the entire universe is actually in a fog. If you've ever been in a fog before, as you look around, you can't see very far because as the light is trying to get to you, it hits water instead, water that's in the air, and either scatters or is absorbed. So you can only see a short distance around you in the fog. The same thing actually happened with the universe. Light is not traveling freely, and so it's not actually possible to see at any great distances. However, as the universe continues to expand, it also continues to cool, and around 380,000 years after the Big Bang, the universe cooled off enough that electrons are finally able to bond to the nucleus, creating atoms for the first time. This period where we're forming atoms for the first time is known as the period of recombination. As this happens, light is then able to travel freely. Because we now have neutral atoms that are not interacting strongly with light, light travels freely. What this means is that the oldest light that it is possible for us to see comes from the period of recombination, around 380,000 years after the Big Bang. This light is the cosmic microwave background, which we mentioned previously. So it's not exactly light from the very beginning of the universe, it's about 380,000 years after, but it is the first light that it is possible for us to see. All light before that had been scattered and interacted with, but at this point, light is now traveling freely. The cosmic microwave background actually contains huge amounts about the formation and evolution of the universe. Now that atoms have formed, we have entered into the era of atoms. Now, during this stage, the entire universe itself has cooled off enough it's no longer glowing. If you remember previously when we talked about continuous radiation is light given off from a hot object. We always compare it back to the burner on an electric stove. Well, during this early stage of the universe, the entire universe itself was so hot it was actually glowing. At the era of recombination, the first light that it was possible to see, the universe was so hot it was orange in color, which I love that we can define exactly how hot and therefore what color the universe was. But the universe continues to expand and cool, which means all of that light is now redshifted and it's not hot enough to produce its own light. And also, because the largest structure we formed at this point is the atom, there are no stars. So because there's no more light, this is sometimes referred to as the dark ages of the universe. Now, one thing we can say is absolutely going on is gravity is acting. It's going to be pulling these atoms together to form into the first proto-galactic clouds. Here is our third lecture quiz question. What are the two forces that determine if a star can form? A. Gravity and the strong force. B. The strong and weak force. C. Gravity and pressure. Or D. Pressure and the weak force. Go ahead and think about it and we'll discuss in just a bit. So what are the two forces that determine if a star can form? It is C, gravity and pressure. Remember, gravity is always pulling things together, and pressure is trying to push out to blow things apart. So we have to have gravity greater than pressure so that it can collapse and actually begin to form stars. So we get this idea that we have to have these regions of higher density for them to be able to collapse. But as they collapse, this is going to increase the temperature, which leads to a rise in pressure. So we're going to have limits on the scale of these higher density regions that will actually be able to collapse and form into stars. If they're too small, there's not enough gravity and pressure keeps them from collapsing. If they're too big, they collapse too fast, heat up too much, the pressure increases, and they dissipate again. So there's going to be this right scale where it's going to be able to continue to collapse. When we apply these ideas to very early universe, the scale, the lengths, and the masses that we get that are going to be able to continue to collapse are the masses and sizes for globular clusters. If you remember previously when we talked about globular clusters, we mentioned that these are very old. And it is possible that these could be some of the very first things to actually form within the universe. Here is our fourth lecture quiz question. What is a population 2 star? A star with a high abundance of metal. B, a star with a low abundance of metal. C, a star with a low abundance of hydrogen. Or D, a star with a high abundance of hydrogen. Go ahead and think about it and we'll discuss in just a bit. Alright, do you remember the different populations that we learned when we talked about the Milky Way? So population 1 are young and relatively metal rich. Population 2 are old and metal poor. So the correct answer is B, a star with a low abundance of metal. So although we see that globular clusters are old, in fact they're very old, dating as far back as 13 billion years old, they do still have metal. Well, the only elements produced during the era of nucleosynthesis were hydrogen and helium. Technically, there were trace amounts of lithium, but what we mean by trace is so little that it doesn't really matter. Okay, so it was just hydrogen and helium. And yet, we see that these population 2 stars have some metal. This means that there must have been a generation of stars before the population 2 stars. We refer to these ones as population 3. Yes, I realize it's backwards. Population 3 are the oldest and first generation of stars, then population 2, and population 1 is the youngest generation. I know, I'm sorry. We started defining things before we actually knew what was going on, but now we're stuck. So these population 3 stars are the ones that should be just hydrogen and helium and nothing else. As we've looked through the universe, we've tried to find these population 3 stars, and we have yet to be able to find them. This has actually led to some ongoing questions. Now we have our fifth lecture quiz question. Which stars have the shortest lives? A, low mass, B, high mass, C, neutron stars, or D, main sequence stars? Go ahead and think about it and we'll discuss in just a bit. Alright, so what type of star has the shortest life? It is B, high mass. High mass stars have the fastest fusion rates, so they burn through the fuel the fastest. So the reason I bring this up is based off of computer simulations. To form a star from just hydrogen and helium with no metal, these stars have to have masses from 30 to 1,000 solar masses. What that means is these are absolutely and definitely high mass stars. That is part of the explanation for why we don't see any of these in the modern universe. If all of them had to form with super high mass, then they lived a very, very short time, and when they died, they spread out the metals so that the next generation of stars would then have a little bit of metal. Another possibility is some computer simulations suggest, although you get one really high mass star, there could be lower mass stars that are actually able to form. Kind of like planets around a star, but here we're dealing with small stars around really big stars, but kind of the same idea. Those low mass stars could still have lived to now, and yet again we don't see any population 3 stars. Something that may have happened to those low mass stars is that they may have been contaminated. When that central high mass star exploded, it would have showered the lower mass stars with metals. So, although they were technically population 3 stars, they look as though they're population 2. Now, exactly what is the exact case here, we don't know. This is an ongoing question. Now, although we have never actually seen a population 3 star itself, we do have evidence that they exist. Not just the fact that there's metals in the universe, but the Spitzer Space Telescope, which was an infrared light telescope, one of the first things it did after launch was to take this image here in the middle. This is a picture of the infrared universe. In it, all of these gray blobs, those are actually stars and galaxies that have been removed, but we see that there's an ongoing infrared background. That infrared light, that infrared background that we see, could actually be the light from these stars. Now, when it was first emitted, it would have been off in the ultraviolet, but because these stars are so far away, the light has taken so long and has been stretched out so much that it's now in the infrared. Now, one thing I want to point out, we only have one of these images. It's only ever been done once, so we don't know exactly, but it's interesting that it is there. Now we can start to talk about how it is that structure formed in the universe. Once we begin forming stars, we've now entered into the era of galaxies. Based off of what we see in the cosmic microwave background, we have some regions that are higher density and some regions that are lower density. Higher density regions are going to sweep together and collapse. These are going to eventually form into the clusters and filaments within the large-scale structure. The places of lower density will have material sweep out, and these will eventually form into the voids that we see today. We can actually create computer simulations. We take the data we get from the cosmic microwave background, use that as the beginning of our computer simulation, and then we put in all of the physics so that the computer can run with all of the correct data and see how it is that the universe has formed. This then allows us to tweak and change different parameters to help us get a better feel for what's actually going on in the universe. Well, as we do this, these computer simulations show that we start with small galaxies that sweep up together into larger galaxies. This is what we call a bottom-up formation. And this is exactly what we see. When we look at the very most distant galaxies, we do not see spiral and elliptical galaxies as we see today. Instead, we see a whole bunch of dwarf irregular galaxies that are close together, and many of these appear to be in the process of merging, colliding together, forming into the larger galaxies, which will then eventually form into the spiral and elliptical galaxies, as we mentioned previously.